second application of diode, we said it as a rectifier. So I said very clearly, what are rectifiers? The conversion of alternating current to a direct current. This involves a device that only allows one-way flow of electrons. It means direct current, a unidirectional current. So that is nothing but an alternating current changing into a direct current is called a rectification, or we can say it is a rectifier. So here we see the first symbol. This is an alternating current, a sinusoidal wave. This is a sine omega t. We can say that y is equal to a sine omega t. Displacement, if you ask to find it out. So this is a sinusoidal wave because it is sine. It is starting from the zero, from the mean position, and half wave in the sense only for the positive half cycle it is rectified, and for the negative half cycle there is nothing, and again for the positive half cycle there is an output, so this is called half wave. And for a positive half cycle of the AC, for the first negative half cycle of the AC, it is also rectifying, so continuously you'll get an output, so this can be called as a full wave rectifier. We'll see in depth to that. Rectifiers, two types of rectifiers we have. The one is half wave rectifier, the other is full wave rectifier. Again, if you see the full wave rectifier, that is again divided into two parts, two diode full wave rectifiers, and the other part is bridge diode full wave rectifier. Simply this can be called as a bridge rectifier, and that is called as a full wave rectifier. We can name it in that sense also. First we will see what is half wave rectifier. This is how it's happening. A half wave rectifier is a circuit that converts an alternating current to a pulsating DC. We are using again and again pulsating DC because if the output what we get as a DC signal will be a mixture of AC also. It is not into the power of form of pure DC form. So that's the reason we say it is in pulsating DC signal. So see this half wave rectifier, the input to the rectifier is in AC and the output is in this form. See, only for the first positive half cycle there is an output. For the next two for the first negative cycle there is no output. It's a plain, and again output, no output, and again. So we can say that this is an half wave rectifier. The rectification is half, only making into the half value. See this, during the conversion process, AC alternation of one polarity are passed to the output, while the alteration of the opposite polarity are blocked. The name half wave is derived from the fact that half the alternations are passed to the output. We can see the same again. Half wave rectifier is shown, and here we have a symbol. This is a PN diode. Only one diode is used. This is an AC symbol. And this is a load resistance across which we measure the output. A diode, which is a device that passes current when the anode A is 0.7 volt more positive than the cathode, blocks current when the cathode K is more positive than the anode. A resistance across which an output voltage is dropped when current passes through it. What is happening? Let's go the operation and the construction of the diode. During the positive alternation, the diode is forward biased, which means the anode is more positive than the cathode. While the diode is conducting, the positive alternation is dropped across the conductor. I'll just explain this. So here what happened is, this is an AC symbol, and this AC symbol we have taken as in first positive half cycle. This is 0.7 volt. This is the only positive half cycle. And this, the black we indicate as a negative. So red stands for positive, black stands for negative. This will call as in one complete AC cycle. First half positive cycle, first half negative cycle. So what is happening when we give a first half positive cycle to a diode? But when we give the first half positive cycle to the diode, this P-type material, as we have connected the P-type material, this particular P-type material will become positive, and this particular terminal, if I label it as a terminal, like we are using a transformer. So secondary coil, the upper part will become as a positive and the lower part will become as a negative. So because this is a positive, we can see the AC symbol, this positive and negative. So the positive when it is connected to the P type and negative of the polarity is connected to when N type, then we can say that the diode is into conducting stage, or the diode is in forward bias. When it is in the diode is in the forward bias, the current will be flowing in the circuit. So for the first positive half cycle, there will be an output like this form. Now what's happening when I give a first half negative cycle? This is the first half negative cycle. So what will happen? So for the first half negative cycle, the point A, if I say this is a point A and this is a point B, so the point A will become negative and the point B will become positive. So this terminal of the secondary coil, if it is a negative, then the negative is connected to the P-type material, and this is a positive, the down one, the down point. This is positive, the positive is connected to the N-type. It means when P-type material is connected to the negative polarity and N-type material is connected to the positive polarity, it means it is a reverse bias condition. And as we have studied, in the case of reverse bias, there is no current in the circuit. So that's the reason the output in the case of half-wave rectifier will be only when for the positive cycle of the AC signal. So for every negative cycle of the AC, the diode, only one diode which we are using in the circuit, will become non-conducting. It means there won't be any current for the every negative cycle of the AC. So that's the reason this is called in half-wave rectifier. And the rectifier efficiency in the case of half-wave will be 40%. So obviously this is not used at all because the signal itself is converting into a half only. The second part we call it in full wave rectifier. So what is full wave? Can produce ripple voltage during both positive and negative input cycle. And there are two types. One is called full wave rectifier. Normally it is called in two diodes full wave rectifier. In the case of half wave, we have seen we have used only one diode. And here in the case of full wave, we use two diodes. So two types. One is called two diodes full wave rectifier and the other is called bridge rectifier. We'll see why we normally avoid to use a full wave rectifier. Everywhere we use only bridge wave rectifier. We see the drawbacks of the full wave rectifier. First, let us go with a two diodes full wave rectifier. And this is how it happens. The full wave rectifier is the equivalent of two half wave rectifiers. In other words, diode D1 will allow current to flow during the positive half of the AC sine wave, and number diode 2 will allow current to flow during the negative half cycle of the AC sine wave. Both provide positive going VP to the load. Now, you just understand with this figure. We'll come back. See, from here you can understand or see the graph. This is V versus instantaneous time T. So this is an AC signal. This is how the AC signal is happening. And here we see that, full wave for every positive half cycle as well as for negative cycle, it is the output is there. So this is called full wave rectifier. So only difference between that and this is, we need to use for the construction, we need to use two diodes, D1 and D2 in this form. And the connections are given in this form. I'll explain the construction, the principle of this particular full wave rectifier, two diodes full wave rectifier. Now see, this is the construction. A full wave rectifier with two diodes and a 1:4 step-up transformer is shown. This is 1:4 step-up transformer. It produces pulsating DC voltage across the load resistance. Now just see that, try to understand this. This is a symbol of a transformer. This is a primary coil, the first coil, and the second one is the secondary coil. To the secondary coil, we have connected one diode. And again, what we did is to the secondary coil of the other terminal, we have connected another diode. Both the cathodes are made short, you can see here. And after making this two cathodes short, we have taken one terminal from here and we have connected a load resistance. And the other part of the load resistance, we have to connect to the center tap of the secondary coil. This is how the connections are made. What is the how it behaves? If you see the, if you see the operations now, what will happen? See, this is a transformer again, a primary coil, a secondary coil. This is first for the positive alternation. The following circuit conditions exist when the positive alternation of the AC supply voltage is applied to the transformer's primary. Now it means that if you see this particular secondary coil, this particular point A, I just label it as an A, the upper part, and the secondaries of beneath part I label it as an B. So the point A becomes positive and point B becomes negative for the first positive half cycle. Now to this particular positive we have connected a diode, and for this negative we have connected a D2. Both the diode cathodes are made short, and from here we taken a load resistance, and this load resistance ended with connecting to the center tap of the transformer, secondary coil of the transformer. Now see, diode D1, because this is positive, this P type of the diode D1 is connected to the positive of the secondary coil, and the N type is connected to the negative of the secondary coil. But if you see the diode D2, the negative of the secondary coil is connected to the P type and positive is connected to the N type. So this diode D1 becomes into the forward bias, whereas the diode D2 becomes into the reverse bias. You can see the current. So diode D1 forward bias and the electron current flows from the center tap through the resistor and the diode D1 to top of the secondary. So this is how it happening. See, from the center tap the current is flowing in this manner through the load resistance, and this is how it's happening. This is how it's happening. This is the positive alternation. The negative potential at the bottom of the secondary and the positive potential at the center tap cause D2 to be a reverse bias. If you see this reverse bias, because this is the center tap, from here the diode D2 becoming into the reverse bias, so there is no flow of the current at the output because of diode D2. So whatever the output we got it, that is only because of D1. So for the first positive half cycle, diode D1 is conducting and diode D2 is non-conducting, and the output is there because of the diode D1. Now for the first negative half cycle, what will happen? This is a negative alternation. The following circuit conditions exist when the negative alternation of the AC supply voltage is applied to the transformer's primary. Here you can see that, see the secondary, the first point, we can say that the top of the secondary is negative and the bottom of the secondary is positive. So the top of the negative is negative, and this negative is connected to the positive of the D1, the P type of the D1. Similarly, here if you see that the bottom of the secondary, as it is become into the positive, this positive is connected to the negative of the D2. It means when positive, this positive terminal is connected to the negative, this positive is connected to the P type of the diode D2, and this negative is connected to the P type. So diode D1 is becoming into a reverse bias, whereas diode D2 we can say it as a forward bias. So for the negative cycle, for the first negative cycle, there will be an output because of the diode D2. Now let's see here again, we'll just go with the line. D2 is forward biased and electron current flows from center tap through the resistors and diode D2 to the bottom of the secondary. The negative potential at the top of secondary and the positive potential at the center tap causes D1 to be reverse biased and to block the current flow. So we can see the cycle, how the current is flowing over here from the center tap here. So from the center tap, because this have made into the diode D2 into the forward bias, this is how it is going in this way through the load resistance, and then it is passing through, and this is how it is, completing the cycle. So in the case of two diode full wave rectifier, for each cycle, no matter whether it's a positive cycle or the negative cycle of the AC symbol, there is an output, the rectification is happening. First, for the positive, we say that the D1 is conducting, D2 is not conducting. For the negative cycle, D1 is non-conducting and D2 is conducting. So this output, if you see here across the load resistor, This is because of the D1 and this is because of the D2. So this is called as a full wave rectifier. So the polarity of the alternation of the rectifier circuit is positive because the current flows through the load from bottom to the top terminal. By reversing the diode connection, the current flows through the load resistors from the top to the bottom terminal and produces DC supply with a negative polarity. This is how it's happening. 2 diodes full wave rectifier. We have already understood. Forward bias and reverse bias. Same thing. This is reverse bias. This is forward bias. Okay. Now we will see the full wave bridge rectifier. Bridge in the sense we will be using here the 4 diodes instead of 2. This is an example of a bridge diode. So why we are going for a bridge wave? Why we are unnecessarily using 4 diodes instead of when we say that to use only 2 diodes? The maximum efficiency in the case of 2 diodes full wave rectifier is 80%, and even in the case of bridge wave rectifier, the efficiency, the output, what we find it out is also efficiency. And what is the meaning? What is the fun to use a bridge wave then? If I go back to this slide, here we have connected a center tap. So the load resistance is connected with 2 points, making short of these two things. Then the other terminal of the load resistance is connected to the center tap of the secondary coil. So physically, practically, it is not possible to get the center tap of the secondary coil. It is highly impossible to exactly get that particular center of the particular coil, so that where the load resistance is connected. So to avoid this practical problem, to identify the center tap and giving a connection, we have a bridge wave rectifier. Efficiency is same. In the case of full wave and the bridge wave, the efficiency is same. So this is how the connections are made. Now see, a full wave bridge rectifier is designed to convert an AC sine wave to a full wave pulsating DC. Full wave. It means for the first positive half cycle and for the first negative half cycle, it will be converting an output. The bridge is normally connected to the secondary of the transformer as shown in figure. See the connections. This is a primary and this is a secondary, and this bridge connection is connected to the secondary of the coil. And here is a load resistance between these 2 points. This is made to the earth, these 2 points, and this is how the load resistance is connected. The discussion of the operation of this circuit will be performed using a conventional current flow. Current will flow from a point with a higher potential to a point to a lower potential. Always the current flows from positive to negative. During the positive half cycle, you can think of the circuit being equivalent to the following. This is how it looks like for the positive half cycle. Then, since the top of the battery is positive, now see, it is the higher potential, current flows from point A to B. Now, we are just imagining if there is a secondary coil. This is just an imagination of the secondary coil. And the secondary coil, top of the secondary coil will become the positive, and the bottom of the secondary coil will become a negative for the first positive half cycle. So this is just an imagination. We are not applying an DC source. It's an imagination of the secondary coil only. So please keep that into the mind. So since the top of the battery is positive, it has the highest potential. Current flows from point A to B. So this is how the current is flowing, because the current flows from higher potential to lower potential. So the current is flowing in this circuit in this manner from A to B. Now what will happen after A to B? The point B will be at a higher potential than point C. It means this point B is becoming positive. Okay? And this bottom point is become negative. So this is a positive. And the current flows from positive to negative. So this is flowing from B to C. As the positive of the polarity is connected to P type of the diode D3, this diode D3, we say it is a conducting, or this is into the forward bias. So please try to understand, please try to observe this diagram point by point. Point B will be at a higher potential than point C. Diode D3 will be forward biased and will conduct current. Point E will be at a lower potential than the point B. So when this is a point positive, this E is nothing but a negative one. Diode D1 will be reverse biased and will not conduct current. So now just see that because the point B is positive, the point E is negative. So the B is positive in the sense this positive is connected to the negative of the diode D1. It means if the positive of the polarity is connected to the N type, the diode D1 is into reverse bias. So there is no flow of current because of the D1, but will be an output because of D3 up to here, up to B to C only. Now see the next part. Now point C will be at a higher potential than the point D. So this is positive, C is positive and this is negative. Current will flow through the load resistance. We can see that there is a current because of the load resistance. So I can say that for the first positive half cycle, there is an output and that is up to here, up to this level, that is because of the diode D3. So point C will be at a higher potential than the point D. Current will flow through the load resistance. The load voltage will have the same polarity. So if you observe the load voltage across this particular, because voltage is always across parallel to the load resistance and current is always measured in series with the particular load resistance. Then now current will flow through the ground connections from point B to point E. Now what is that? Because point C is at higher potential and we said that there is a current through the load resistance, the current will flow from point D to E, this manner, D to E. So it is flowing from point D to point E. Now when I say that the current is flowing, it means the positive, it is flowing from higher potential to the lower potential. Now see what will happen. Point E will be at higher potential than the point F. Can you see that? Can you see that when the current is flowing through the load resistance, I'll go back to the previous slide. From point D to E, what will happen to the point E? Point E will be at higher potential than the point F. See, earlier I said that the point E is negative with comparative to the point B. But if I compare the point E to F, the point E is at higher potential. Diode D2 will be forward biased because this point E is positive and this positive polarity of the battery is connected to the P type of the diode D2. So this again diode D2 have become into the conducting stage or can be called as a forward bias. So diode D2 will be forward biased and will conduct current. Point B will be at higher potential than the point E. Diode D1 will be reverse biased and will not conduct current. Then, so what are the two diodes for the first positive half cycle which are conducting stage? Diode D3 and diode D2. Now, current will flow back to the negative terminal of the battery. Point F is at a lower potential than the point C. As we have seen, this point F will be at the lower potential than compared to the point C. Diode D4, if you see this is a point C, this is the point C. Diode D4 is reverse biased because this is at a lower potential. It means this is negative polarity of the battery. So this negative polarity of the battery is connected to the positive of the battery. So this is reverse bias. So diode D4 is reverse bias and will not conduct any current. Now next what will happen? So summary, if you see the summary, for the first positive half cycle, diode D3 is forward bias and diode D2 is forward bias. So load voltage is positive. For the first negative half cycle, diode D1 is forward bias and diode D4 is forward bias. So the load voltage here is positive. And the output of the waveform will appear like this. So for each cycle, no matter whether it is a positive or negative cycle of AC input, there is a DC pulsating output. So this is called a full wave, or this is called as a bridge wave rectifier. And why we use a bridge wave rectifier instead of two diodes full wave rectifier? To just avoid the center tap of the secondary coil. This is all about rectification. Now, as we are saying that, the output is into the DC pulsating form. So to remove that particular AC mixture into the DC voltage, we use a filters. Circuit that converts the pulsating AC voltage to a DC voltage. The main function of the filter is to reduce the ripple into the input waveform. We have different kinds of filter. Capacitor filter is very popular because of its low cost, small size, lightweight, and good characteristics. This is a kind of a filter. I'll not go much to this. This is kind of a filter. Okay, I just named that as an. We have seen the rectification. We have seen the two types of rectification and the filters. Generally, a rectifier is used to produce pure DC supply. However, the output of the rectifier has pulsating character. That is, it contains AC and DC components. The AC component is undesirable and must be kept away from the load. So a filter circuit is used which removes the or filter out the AC component and allows only the DC component to reach the load. So that's the basic definition of a filter, which is removing the AC pulsating and then only providing us with a pure DC form. There are types of filter called as an capacitor filter, which can be called as a shunt capacitor filter, choke input filter or LC filter, capacitor input filter or pi filter. So there are 3 or I think 4 types of filter we have, where which we can avoid AC pulsating and get the output into the DC form. So this is called as an shunt capacitor filter. This is one type of filter. This is how it happens, and slowly we can see that the output is into the pure DC form. This is nothing but this is called as an pi section filter. 2 capacitors are used and 1 inductor is used. So capacitor input filter or pi filter, this is called as see LC filter. Then the other is shunt capacitor, choke input filter, and RLC filter. Okay, these are the few filters what we have. Then the voltage regulations. Zener diode basically is used for the voltage regulation. Let us see for this example. The functioning of regulation is nothing but stabilizes the output voltage. Why we use a stabilizer at home? Because of the fluctuations, because of the raw materials used for the generation of the power, or because of the weather condition, or because of the unforeseen conditions, weather conditions and all. The fluctuations of voltage happens from 220 to somewhere also it goes shoot up to the 300 voltage. And all the home appliances, any electronic gadgets or leave about the electronic gadgets, all the home appliances only can take up to the 240 or 260 or up to that level only. Once we cross that particular voltage into the higher value, definitely a malfunction can happen. It can corrupt your appliances, and anything can go wrong with the appliances. So we need basically a stabilizer. The input to the stabilizer is given from 220 to 2 voltage, any fluctuated voltage. But no matter what voltage you give as an input to the stabilizer, the output should be constant. It should be only 220, so that it will safeguard my home appliances. So the function of stabilizer is nothing but stabilizes the output voltage, reduce the ripple at the output voltage of the filter circuit. So for the voltage regulation, we use a Zener diode. How the Zener diode is made? The Zener diode is made with a heavily doped. The difference between PN and Zener is how the Zener is made in the sense by doping. If you dope it heavily, then the Zener is formed. Or we can say that the definition for the Zener is a properly doped crystal diode which has a sharp breakdown voltage is known as Zener diode. So this is a symbol. It looks like a Z, not exactly Z, because exactly Z stands for the other symbolic representation of the diode. So Zener diode is a silicon PN junction devices that differs from the rectifier diodes, a normal diodes, because it is designed for the operation in the reverse breakdown only. One Zener diode connected with one resistance and a battery. That is a basic circuit. A source, you have a resistance and a diode. So we can see that the positive of the battery is connected to the negative and the cathode. It means this diode is connected into a reverse bias. Normally, what is Zener diode? If you see that, then a Zener diode is like an ordinary diode, except that it is properly doped, so as to have a sharp breakdown voltage. It is made, the impurities is added in such a manner to get an output as a sharp breakdown. A Zener diode is always reverse connected, that is, it is always reverse bias. Okay. What are the characteristics? The Zener diode is always reverse connected. When forward bias, its characteristics are just like of the ordinary P junction diode. It has a sharp breakdown voltage called a Zener breakdown. See, here is a graph of the particular Zener diode. This is a forward bias. This can be called as forward knee voltage. So up to here, as the voltage is increasing, the current in the circuit is zero only up to here. Once it cancels the potential barrier, then as you increase the voltage, if the potential difference is more than the threshold voltage, then it is, the current is rising up in this manner. So this is called forward bias region. Forward bias, this is the first quadrant, and similarly minus B and minus I, it means this is the third region. So this is called a constant Zener voltage. You can see here. You can see here, you'll get a constant voltage, no matter if you have the fluctuations on, you will not have the variation of voltage, it will give the constant output. And this is called a Zener breakdown region. They have just shown an example, cathode and anode, and this is a symbol of a Zener because it is connected in reverse, that is shown in that manner. The principles, the working principle of Zener diode lies in the cause of breakdown for a diode in reverse bias condition. Normally there are two breakdowns. One is Zener breakdown and the other is called an avalanche breakdown. Let us study the Zener breakdown. This type of breakdown occurs for a reverse bias voltage between 2 to 8 volt. Even at low voltage, the electric field intensity is strong enough to extract a force. The valence electrons of the atom such that they are separated from the nuclei. This type of breakdown occurs normally for a highly doped diode with low breakdown voltage and larger electric field. As temperature increases, the valence electrons gain more energy to disrupt from the covalent bond and less amount of external voltage is required. Thus, Zener breakdown voltage decreases with the temperature. And the other breakdown is called as an avalanche breakdown. This type of breakdown occurs at a reverse bias voltage above 8 volt and higher. It occurs for a lightly doped diode with a large breakdown voltage. As minority charge carriers flow across the diode, they tend to collide with the electrons in the covalent bond and cause the covalent bond to disrupt. These are the two breakdowns. As voltage increases, the kinetic energy of the electrons also increases. The covalent bonds are more easily disrupted, causing an increase in the electron hole pair. The avalanche breakdown voltage increases with temperature. Now, the circuit for the voltage regulation. They have given a source, then a resistance to protect the circuit for the proper biasing, we can say that, and a diode, Zener diode, and across this particular Zener diode, we have connected load resistance, and across this particular load resistance, we measure the output voltage. So, see this, the construction. In a DC circuit, Zener diode can be used as a voltage regulator or to provide a voltage reference. The main use of Zener diode lies in the fact that the voltage across Zener diode remains constant for a larger change in the current. This makes it possible to use Zener diode as a constant voltage device as a voltage regulator. In any power supply circuit, a regulator is used to provide a constant output voltage. While designing a voltage regulator using Zener diode, the latter is chosen with respect to the maximum power rating, and the maximum current through the device should be I max should be equal to power by Zener voltage. Since the input voltage and the required output voltage is known, it is easier to choose a Zener voltage with a voltage approximately equal to the load voltage. I'll just repeat this one, how this functions. So what happens? A Zener diode can be used as a voltage stabilizer regulator to provide a constant voltage from the source whose voltage may vary over sufficient range. So within that particular sufficient range, if there is a variation of the voltage, but still the output should be a constant. So that is basically called as a voltage stabilizer. The Zener diode of the Zener voltage is reverse connected across the load resistance. You can see that VZ is reversely connected, across which the constant output is desired. We measure the constant output over the RL. The series resistance R absorbs the output voltage fluctuations so as to maintain constant voltage across the load. Therefore, the Zener will maintain a constant voltage. That is, we have seen this one. VZ is equivalent, more or less equal to V0. So this is how the load voltage, we say it. The input is VZ is almost equal to a output voltage. So it is maintaining a voltage regulation. Suppose now what is the other thing? The input voltage exceeds the Zener voltage, the VZ. We can see the VZ. This brings the Zener diode into a breakdown region. So we can see that this is one of the example of the Zener diode as a voltage regulator. And lastly, we can see that the IC voltage also. Integrated chips, what we normally, integrated circuits, what we normally say, the voltage regulation. So this is how the voltage regulator, this is a 7808. We have 3 pins, one is input, the other is output, and one is the ground. We have the three. Normally we say that the two diodes, this is the 3 terminals, one is ground, the other is input, and the other is output. This is particular series, it is working commonly. And this is how the circuit goes, like input and output. And here we have used a diode. This is a IC voltage regulation, and we use this in one integrated chip, and 2 condensers are connected in parallel to each other. And the output, we can see that using an IC, how the regulations happens. So this is how we covered up all the topics which are related to PN junction, then the applications and the different kinds of diodes, how the diode functions, the principle of the diodes into 2 modes, forward and reverse bias, and then all the different kinds of diodes what we have in the applications normally used in, and then how the alternating current can be converted into direct current using the different kind of rectifiers, half wave or 2 diodes, full wave rectifier and bridge rectifier, overcome the center tap of the secondary coil. Then we have used the filters, how the DC pulsating can be removed from the output of the rectifier so that the output will be into the pure form of DC. And then after filters, we have used the Zener. Zener basically used as a voltage regulator. And lastly, we have seen the IC voltage regulator also using that particular 7808, which will be having 3 terminals, an input, an output, and a ground. So thank you everybody. Thank you for listening. So thank you. Next class we will be having the next we will see the topics called transistors. Suppose we have 2 PN diodes connected suitably, then a transistor is formed. Earlier we have seen a 1 PN diode, 1 P type, and the second N type. When P and N type are suitably added, a junction is formed. So what will happen when I take two PN junctions? Then a transistor is formed. Transistors. Esters is nothing but resistors, transforming of resistors. So that is the Latin word of esters. So we will see the next class regarding the transistors and all the configuration of this transistor. Transistors uses an amplifier and oscillators and all the applications of the transistor. So for this, I'm signing off. Thank you.